So far, we have seen two things, right? So first, Alice's new coin game has positive expected value. So in some sense, it's a favorable game. So Alice should be playing it. And second, we saw that betting everything every round is a bad idea because one loss will send Alice to zero, and if she keeps doing that, she's eventually going to go bankrupt with probability 1. So now we ask the question, so how much should Alice bet each round, right? And so clearly 0 is too conservative because then she does not take advantage of the favorable game, but betting everything is too aggressive because it creates too much risk. So we want something in between, and this leads to the idea of something called an optimal betting fraction. So instead of betting a fixed dollar amount, Alice bets a fixed fraction of her current bankroll. So like maybe, every time she bets half of what she has, or she bets a quarter of what she has. And so the goal is to balance growth and risk, right? So one way to formalize this is to maximize the expected growth rate of the bankroll. And so instead of expected dollars after one round, we maximize the expected logarithmic growth. And so the idea is to maximize the expectation of the logarithmic instead of just of the value itself. And so this is known as the Kelly Criterion. And the logarithm matters because repeated betting is multiplicative. So for example, if your bankroll goes up by a factor 1 round and down by a factor the next round, then the long-term behavior depends on the product of the factors, not just the sum of the dollar gains, right? So taking logarithms turns products into sums, and so log growth is a natural way to measure the long-term growth. And so the Kelly Criterion gives a betting fraction that tries to grow the bankroll efficiently while avoiding the extreme risk of betting too much. So let's look at this. So let's compute the Kelly fraction for this game, for Alice's game. So suppose Alice's current bankroll is B, so she starts with B amount, or her current money, so we're looking at the current versus the next step. So she currently has B, and so now she's going to bet a fixed fraction F of B, right? So if F was half, she's going to bet half her money. So what will happen? So if she wins, she gains twice her bet. So this here, if she wins, she gains B plus 2 times. So she had B, and she's going to gain 2 times what she bet. And if she bet this fraction of B, she gains B plus 2FB, and so you can write this, if you factor out the B, as 1 plus B 1 plus 2F, which is exactly what we wrote here. And if she loses her fraction of B, right? So she loses her FB, and this is just B1 minus F. Okay. And so what we are interested in is the logarithmic growth. So we're interested in what happens after she plays. If we take the logarithm of that and subtract the logarithm of what she had before, what we get, right? So if you just write it out and take the logs, you'll get this expression here. The difference is gonna be log of 1 plus 2F with probability half and 1 minus F with probability half. And so the expectation of this, so if you take the expectation of this and compute it, it's just going to be this half log 1 plus 2F plus half log 1 minus F. So just half times this plus half times this, right? And so this is the function we want to maximize. And so let's give a name to this function. So this is our logarithmic growth per round function. It's g of f, and it's equal to this. And we want to find what is the f that maximizes that. So how can we do that? Well, if you go back to your calculus course, this is a one variable function here. Just take the derivative with respect to f and equate to 0 and solve. So if you take the derivative of this with respect to f, you will get this expression here. So go back to your calculus notes and review that. And now you simplify and you get this equation here that you need to solve. And so the idea then is, well, okay, so solve this equation. So if you go around and solve this equation, so of course if you set on both sides and multiply by the denominators, you need to essentially solve this, you expand and so on. And you can find that for this problem, the optimal f is going to be 1/4. So what does this mean? This means that in this game that we're analyzing, what the Kelly criterion is saying is that Alice should be betting 25% of her bankroll each round. And so this is much less aggressive than betting everything, but it still takes advantage of the fact that the game is favorable, right? And so here we can see this function plotted out, so our g of f as a function of the fraction. And what we can see is that if f is too small, then Alice is being too cautious. So here a growth of 0 is just keeping the money that you have in the long term. And so if you don't bet anything, I mean, you don't lose, but you don't win. So you keep at the same. As you increase the fraction, you start to increase by how much you expect to grow over time until you achieve this maximum. And so this is the maximum growth rate that you can have, and it happens at 0.25, right? And now if you start to go over it, you will still have a growth rate above 0 if you're less than half here. So for example, what this is saying is that if you decided, for example, to bet half your money, so if Alice is betting half her money, she would expect with high probability to see a growth rate of 0. So in the long term, she would not be making any money. So anything before that, she still makes money, but here she's making less money than she would at 0.25. And of course, what this shows is that if she were to actually bet more than half her money, then what will happen is that in the long term, her growth is going to be negative. So she's going to lose money if she bets more than half. So of course, this half here is a very important point, because you definitely do not want to lose money. How sad it is that in the long term you're playing a game that is favorable for you, but you're risking so much that you are just going to lose money in the long term. So you definitely want to be somewhere around here, right? Ideally you would like to be here, and you can actually make a point for you actually want to be to the left of this curve. Why? Because to the right, you don't gain more than to the left. And actually here, the more you go to the right, the more variance you're going to add. And that's actually going to be the topic of a different video when we start talking about variance. You want to keep the variance low also. So in general, you want to be betting the Kelly criteria or less, right? Okay. So this example that we saw was for a special case, but you can go and redo everything we did for in general, and you'll get a nice formula. So suppose you repeatedly bet a fixed fraction of your bankroll. So let P be the probability of winning. Let Q be the probability of losing. Let B be the proportion of the wager gained if you win. So what we mean by that is that if you bet $1 and win, you gain B dollars in profit. Then what the Kelly criterion says is that the optimal fraction of your bankroll to wager, so what fraction of your current bankroll should you be betting, is going to be given by this nice formula here. And so in our example, the game that Alice was playing was P equal to half of winning, Q equal to half of losing, and she was making $2 for every dollar she bet when she was winning. And if you substitute this into the formula, you get what we found, which is just the 1/4 here. And so this is a general version of what we just saw. So this tells you in general what proportion of your money you should be betting in games of this form.